Hi, welcome everyone again for the second session. My name is Nathalie van Hout. I'm from the SCK. And together with Caroline, I will share this session. Please.
Good morning, everybody. So I'm Caroline Vigneault from IRSN in France. And we will start with Miquel Vidal from University of Barcelona with a new insight into soprtion and desorption processes of NOR on soils and recommendations for the use of KD values.
Good morning, everyone. If you like, I can share my own screen.
Yes, go ahead.
It works, no? Yeah, okay.
Okay. So, good morning, everyone. I'm presenting this work, which belongs to the task 2.7.2 on behalf of my colleagues from University of Barcelona and also for my colleagues of IRCN. The work has two different sections. The first one is dealing with the creation and analysis of new soil KD datasets for naturally occurring radionuclides. And the second section deals with the influence of the type of contamination and time on uranium retention parameters in soils. So as you know, KD is a key parameter that often is used in risk assessment exercises. And then we need large data sets to be able to derive representative KD values for the scenario to be assessed. So in the frame of this task, we have carried out a gathering of information, of data which is available in the literature, from defining criteria for that acceptance. And we have seen that sometimes it's difficult to find specific information on characteristics of the soil and liquid phases. And for sure, there is a lack of data for certain radionuclides and for certain types of soils, for instance, for organic soils. So we decided to carry out batch experiments to get new KD data on a number of radionuclides, basically uranium, radium, and polonium. So by changing some aspects of the methodology of those batch tests we have applied at laboratory, we have been able to derive different KDs, such as sorption and desorption KDs, or also data from native radionuclide. And also we have tried to fully characterize both solid and liquid phases. So at the end, we have a data matrix in which we have a number of properties such as pH, organic matter, texture, CEC, exchangeable cations, cations in the soil solution, carbonate content, DOC, DIC, etc. And we relate every single property with a KD value for a given soil. So at the end, we have large data sets for these three radionuclides. Now we are dealing with 300 entries for those radionuclides. So now it's easier to try to apply a statistical analysis and try to derive models, both based on multivariate regressions and probabilistic functions. As tomorrow there is a talk dealing with modeling, now I'm going to focus simply on showing just some examples of those functions from which we may derive best estimates of KD. Probabilistic functions based on cumulative distribution functions, CDFs, actually they permit the visualization and exploratory analysis of data sets. For one side, for the 50th percentile, we may derive a best estimate of the KD, and also we may have some information on variability by, for instance, comparing the percentiles, the 5th and the 95th percentiles. For sure, besides working with the overall distribution, with the overall data sets, we may group the data according to a given number of selected variables, for instance, variable based on soil properties or in the experimental approach on the source stem, in order to try to decrease data variability and then to improve the derived KD best estimate. So just a few examples on this approach. For instance, focusing on uranium, here I show you distribution functions obtained from batch tests with freshly incorporated uranium, both based on sourction and desorption approaches. As you may see, we have best estimates around 500 for sourction scenario and around 5,400 for desorption one. If we compare statistically those two populations, we may see they are statistically different. So we may derive a statistical factor of near to 3, indicating that some aging can be occurring, and then the uranium KD may be larger for desorption than for sorption process. A similar approach can be followed for radium. In that case, the values are a little bit higher, and we have like 1,500 for sorption data and around 2,500 as a 50th percentile for desorption data. Again, those two populations were significantly different, and we have an hysteresis factor of around 1.5. For polonium, for instance, that there was a lack of information. We did not observe a significant effect of the approach or of the kinds of KD that was being quantified, as sorption KD and desorption KD populations were not statistically different. Focusing in this example of polonium, we can make a step forward and we may try to see whether the SOSTEM may play a role in KD quantification, and for sure they do. SOSTEM does affect the KD value. So here we compare the overall distribution for the overall data set survey, and we compare with data originated for freshly incorporated polonium and from data from native polonium. As you may see, there is much difference between the KD best estimates with different orders of magnitude. So we have native data that can be as a mean value, as a 50th percentile, as high as 30,000, whereas for freshly incorporated can be, with data in the literature, affected by a large variability, it's true, can be as low as 500. So in that case, this simple approach permits to derive more representative KD according to the SOSTEM. But also we can incorporate although additional factors, like for instance, soil properties. Here also is a simple exercise in which we try to first to separate data according to the SOSTEM. So we separate native on the left and fresh incorporated on the right. And for every single data set, we distinguish subgroups according to organic matter content. The threshold, after testing different thresholds, we use 10% threshold to distinguish between, let's say, organic and mineral soils. As you may see, the KD is very sensitive to this organic matter content, and we may have lower KD values for polonium, dealing with organic soils with respect to that we can be proposed for mineral soils, and with changes in more or less 1.5 order of magnitude for native and around 1 order of magnitude for freshly incorporated sets. So you may see here how different can be the KD playing with these distribution functions and just grouping according to different factors. So it's clear that a single overall KD value is useless for risk assessment exercises. So going a little bit forward in the presentation, another question that we may be asking is whether time may play a significant role, and if we can estimate the impact of soil aging on the KD. So the first question is, can we assume that the KD is constant over time? And the answer is not. We cannot assume that. First of all, as I showed you before, we observed changes in between KD and desorption KD depending on the radionuclides. And also it's well known that there can be a process, this is the aging process, affecting both soil phases and also the possible stabilization of the radionuclide in the soil. So the people from RSCN have evaluated how this aging process can be affected either by the time of contamination or the type of soils. And also they have tried to evaluate whether we may predict retention parameters of recently added radionuclide based on data from native isotope. The work has been focused on uranium. So they have been contaminated 4 different soils, coming from sandy soil to organic soil and mineral soils with different texture. So they've been working with 4 contrasted soils, and they have been contaminated with 2 different source terms. One is uranium in a liquid solution, so it's a liquid contamination, and the second source has been based on a crushed organic matter material. It was the Galax plant, and then we can compare whether this liquid contamination or this organic matter-based solid contamination plays a role in the retention parameters of uranium. So those soils have been incubated for more than 3.5 years, and samplings have been carried out at the initial time, after 7 months, after 12, and finally recently after 42 months. So soils have been incubated at around 28 degrees, and you may see in the picture. So the samples has been analyzed based on a successive batch desorption test that Copin Italia has published in 2023. Basically, what they do is try to in batch tests, they carry out a number of desorptions, around 4 desorptions for the initial contaminated soil, and then they recover every time the solution. So from that, they can apply the classical approach in which the KD is assumed to be reversible. So from the total extraction after the 4 desorption steps, they may quantify a desorption KD and also the percentage of let's say, of uranium radionuclide could be extractable in water. But besides, we linearize every single step of this successive extraction, as the way is shown in the figure, and then by representing the total amount of the radionuclide in the solid versus the solution for every single case, they may derive from the interception, they may derive the, let's say, the non-available fraction of radionuclide, which is in solid phase. And also from the slope, they may derive what they called the available desorption KD. So why those 2 concepts are important? Because in this approach, this alternative approach, which is actually a 2-box model, they distinguish between the fraction of the radionuclides, which is in the solid phase, that is still participating in equilibria with the water compartment, from this fraction, which is no longer participating in equilibria. So with respect to the classical approach, it's a 1-box model in which we consider a reversible KD and we don't make distinctions in the solid phase. And with this 2-box approach, we distinguish between the fraction of the radionuclide in the solid phase, which can or cannot participate in the equilibria. So for this model, the KD desorb, the desorption KD is the available desorption KD, and also we may quantify the percentage of remobilizable radionuclide, this kind of labile fraction. So a summary of the results. For sure, the soil properties affect the retention parameters. Actually, a highest KD was observed for the undersoil organic soil with respect to the lowest KD that was observed for the sandy soil. The type of contamination affected also the uranium retention parameter, and then actually the extractability was generally lower when the source of contamination was a liquid one than when the contamination was organic matter based. And then the retention parameters change with time. although changes dependent on the soil type and also on the time of contamination. So in generally, an increase in the desorption KD was observed over time, with exception of the sandy soil when it was contaminated with the particulate organic matter contamination. Reasons for this lies in the fact that this source stem is affecting the DOC, the dissolved organic carbon status of the soil. So there is increasing this DOC, which is very relevant for the sandy soil that was very poor organic matter. So a small amount of DOC affect the DOC status, and then it's affecting the interaction of uranium, and then it's provoking a decrease in the desorption KD that is overcoming the potential increase due to the time effect. So with this exception, there was a clear increase in the retention parameters over time. Based on the one-box model, the classical model, it was very clear that the desorption KD from the recently added uranium was lower than the desorption KD based on the native uranium by a factor that sometimes was of one order of magnitude. The same was observed with respect to the water extraction, that the water extraction was much higher. Again, this one of magnitude was much higher, as you may see in the figure on the left, back on the left. So you may see that water extraction with recently added uranium was much larger than that from the native uranium. So clearly, we could not predict any behavior of the recently added uranium based on the native uranium, and if we apply this classical desorption KD model. But if we apply this two-box model, for one side, we can see that if we take into account in the data set all the soils sampled over the 4 times, etc., and we create this kind of population, and we compare that the available desorption KD from the recently added uranium with respect to the native uranium, we see that there is a beautiful correlation with a slope near to 1. So those two KDs were comparable, and whereas there was also correlation between the removable fraction, although here the slope was around 10, so there was this factor of 10 comparing the labile fractions. So the labile fraction for the recently added uranium was like 1 order of magnitude higher than the removable fraction for the native uranium. But it's true that we can predict the available desorption KD of the recently added uranium based on data from the native uranium. So just to finish, just simple messages that are very obvious, but I like to finish with these kind of recommendations. So for one side, we need to have large data sets in order to be able to elucidate soil properties governing norm interaction, and then eventually to be able to derive models to predict KD. That although we have been able to enlarge the data sets for radium, for polonium, and for uranium, still there are some gaps that are being identified. So sometimes we observe that the soil properties ranges are still narrow, or still there are some data missing, that, for instance, organic soils. So again, efforts should be done for enhanced data sets in order to improve model calibration sets. Has been observed, as we always knew, but it's been confirmed, that the use on an overall single KD for a target radionuclide for any scenario is not recommended due to the high associated variability. Then reliable KD values to be used have to be taken into use in assessment models, have to be taken into account the scenario to be assessed. So it's not the same to compare fresh incorporated versus native radionuclide, or soil characteristics, or the source term of the contamination, aging, time dynamics must be taken into account. So we have to make an extra effort to characterize the scenarios, because with this kind of key information, we cannot do a proper assessment exercise. And finally, as the source term is so important, depending on the source term, the KD of a given radionuclide can be different in a soil. So when we are facing, for instance, the scenario of the leaching of non-materials affecting not contaminated soils, this leaching must be characterized in order to have a proper information on the source term in order to be able to predict a reliable KD for this assessment exercise. So this is all. Thank you very much. Thank you very much for your attention.
Thank you. Thank you very much for this great informative presentation, Miguel. Are there questions in the audience or online? I don't see any questions. No questions. I have a small question, and it's more related actually to the fact that now it's all based on soil research that you do. But when we talk about norm or naturally occurring radionuclides, we often also and also risk assessment, we come to the case where you sometimes have matrices or materials that are not specifically soil. How do you see that within the concept that you just presented?
Yeah, thank you, Natalie, for your question. Well, I actually have focused only on soils, but our data sets also include data from sediments. We also have data from organic rich materials such as biochars, for instance, and other similar environmental matrices. So we have carried out some statistical analysis that sometimes they show that they are not a significant effect over the pattern behavior that is more significant than effects caused by properties. So either you have a sediment or either you have another environmental matrix. Once you have, I don't know, organic matter content, the pH, or information of competitive cations, DOC, for instance, then the pattern behavior that we are trying to predict behaves the same. So other properties such as the source term, the time effect, or the actual edaphological properties play a major role than the nature on the type of environmental matrix. But there is still a lot of work to do with materials themselves. Like, for instance, you have experience with those calcium fluorides or another phosphogypsum and so on. So those are challenges matrices to be analyzed. And this is for the future, I'm afraid.
Okay, but to clarify, these data were not included in the database that you made, huh? Or
not for the batch, for those in which we have batch experiments, but data is included in the large data sets in which we have included literature data.
Okay, thank you. Thank you very much. Thank you again.
You're welcome. You're welcome.
Thank you.